All right. Next up, we've got lone pairs. So with lone pairs, we don't have to show them, but they're still there. And so we need to know when we have lone pairs, when we don't have lone pairs, even though they're not explicitly drawn, we have to know where they're at because that's where a lot of the action happens. So anytime we really want to figure out how many lone pairs there are, we can do it kind of the long way, and that's with calculating formal charge. So that's Fc here is formal charge, and that's equal to the number of valence electrons the neutral element has, or basically which column in the periodic table it is, then minus the number of bonds that it has, minus the number of lone electrons, right? Not lone pairs in this case, but lone electrons. So let's take a look at an example. Classic water. And we're going to take a look at the central oxygen, right? So we don't see any charge on it, so its formal charge is equal to 0. Oxygen is in the sixth column, so it has 6 valence electrons when it's by itself. Here we have 2 bonds. And then what we're trying to figure out, our X or our question mark here, is how many lone electrons it has. And so then when we reorganize to solve for our question mark, you should get 4 lone electrons. And that's lone electrons, so that means 2 lone pairs, right? Because there's 2 electrons in each lone pair. So this is how we draw water in organic chemistry. However, we know that in reality, it has those 2 lone pairs. We just don't like to draw them in. Saves us a little bit of time. Let's take a look at another form of oxygen in hydroxide, right? So now we have an OH with a negative charge. So in this case, the formal charge is equal to -1. Oxygen always has 6 valence electrons when it's by itself. Here now we're reduced down to 1 bond, and then our X right there, or our question mark, will be how many lone electrons it has. When you solve for the question mark, you get 6 lone electrons. And then if we think about that, that reduces down to 3 lone pairs. So in hydroxide, we have the oxygen with 3 lone pairs. Again, we don't have to draw these, but they are there. So that's kind of the mathematical way to figure out how many lone pairs there are. However, through organic chemistry, as I'm sure you've experienced in the first semester of organic chemistry, there aren't really that many different elements that we use, and so there's not many motifs there. So you kind of just memorize them or just know what they are through use. So our main elements are carbon, hydrogen, nitrogen, oxygen, and then X for our halogens, our chlorine, bromine, that kind of stuff. So hydrogen does not obey the octet rule, right? It only wants 2 lone electrons, 2 valence electrons, or 1 bond. So when you see hydrogen, it might only have 1 bond. And then this R right here just means something else. Maybe it's a carbon, maybe it's a hydrogen. It's just bonded to something else. So when hydrogen has 1 bond, it has no lone pairs. Another common form of hydrogen is our proton, or H plus. In this case, it has no lone pairs as well. And then finally, we have the hydride, the H minus. In this form, it does have 1 lone pair. Next up is carbon. Carbon most often has 4 bonds, right? So carbon bonded to 4 different things. And in this case, it has no lone pairs. Note that when I'm talking about 4 bonds, I don't know, whether they're double, single, triple, it doesn't matter, just as long as the total count is 4, right? So in both of these examples here, carbon has 4 bonds, no lone pairs. Another common form of carbon is our carbocation. So in that case, it has 3 bonds and then a positive charge. In that case, it does not have any lone pairs. And then we can have the opposite, our carb anion, in which case the carbon has 3 bonds and a negative charge. In this case, when it has this negative charge, it does have a lone pair there. This is relatively rare, so we won't see too much of it. Next up, nitrogen. Nitrogen most often has 3 bonds and is neutral. When it has 3 bonds and it's neutral, it has 1 lone pair. Another common form of nitrogen is 4 bonds, in which case it has a positive charge, and in this case, no lone pairs. And then finally, we have nitrogen with two bonds and a negative charge. In this case, it has 2 lone pairs. This is also relatively rare. We've used it a little bit in first semester OChem, but not too much. Next up, we've got oxygen, which we've already gone over a little bit. Its most common form is with two bonds, no charge, and in that case, it has two lone pairs, as we've seen. Another common form of oxygen is with three bonds and a positive charge. In that case, it only has one lone pair. And then finally, our oxygen with one bond and a negative charge. In that case, it has three lone pairs. And then finally, we've got our halogens, and these are chlorine, bromine, iodine, and fluorine. Most oftentimes, they just have one bond, in which case they do have three lone pairs. Most oftentimes, these lone pairs don't really do anything. And then finally, we have the halogen by itself, in which case it has four lone pairs. And I forgot, it has the negative charge as well. So again, with these lone pairs, there's something that really important in organic chemistry because the electrons are what do the actions. We can calculate formal charge to these equations, but most often you're just going to use these compounds so much, these elements so much, that you're probably just going to memorize how many lone pairs they have through use, and you should just be able to look at a element in a molecule and identify relatively quickly how many lone pairs it has.